Good morning, everyone. I'm very appreciated to speak here and very happy to share my work with you. I am Zhu Ziqi, the first author of this work. This work is collaborating with this author. Today's topic is about registry ABE via predicate encodings. The registry ABE is an extension of standard ABE to avoid TX problem. And all work than the first generic level construction of registry ABE. First, I'd like to give a brief review about ABE. It provides fine-grained access control for encrypted data. The attribute-based encryption consists of four algorithms. In setup phase, it takes us into a description of predicate and return a master public key and a master secret key. With the master public key, anyone can encrypt the message, and the ciphertext is associated with the value X. Use the master secret key. There is a key center to generate the secret key for the user with some value Y. In decryption phase, a user with value Y can use this secret key to decrypt the ciphertext with value X. And if the predicate TXY equal to 0, the decryption fails and cannot recover the message. Only if the predicate equal to 1, the decryption can go through successfully. Now I'd like to move on to the registry ABE. It's an extension of standard ABE, and instead of key center, it allows user to generate the secret key itself. And thanks to the blueprint in HFLWW23, we can focus on a weaker primitive called slow-T registry ABE. The slow-T registry ABE consists of 6 algorithms. In setup phase, it takes us into the description of predicate and the number of slots, and return a CRS, which is public for all users. With the CRS, the users in each slot can generate its key pair itself. And before the registration, it needs an algorithm to make sure that the public generated by user itself is valid. In aggregate phase, each user will submit its public key along with a value Y to the aggregator. After collecting all public key and the value Y, the aggregator can generate a master public key for encryption and give back the hyper key to each user, which will be used in decryption phase. The encryption phase is similar to that in standard ABE. The encrypted data will be associated with some value X. In decryption phase, a user with value Y will use this secret key and the hyper key to decrypt the ciphertext with X. And same as the standard ABE, the decryption goes through if and only if the predicate PXY equal to 1. Now we are concerned about what is the security of registry ABE. And let's look at the security model in the 3-slot setting. At the beginning, the challenger will generate a CRS and give it to the adversary. After getting CRS, the adversary is allowed to make queries to these two kinds of oracle. We call them oracle generate and oracle craft. The challenger will keep 3 dictionary and a property set to record the answer to this oracle. In oracle generate, the adversary can ask for slot index. And take a look at this. The challenger will generate the key pair for this slot I and record them in corresponding dictionary. the public key to the in property set. In Oracle prop, the adversary can ask for the secret key corresponding to a public key of sort I that was getted from Oracle generate. As you see, the challenger will look for the corresponding secret key from the dictionary and record the tuple I and public key into property set. And the adversary can repeatedly make queries to these two oracles. In challenge phase, the adversary submits a value X and to challenge message, such as in standard ADE. In addition, it will submit a series of public key and values. With challenge public keys, we consider three cases of slot. The first one is the property case. The public key was given in Oracle generate but was asked in Oracle prop, which means this public key is generated by the challenger, but the adversary knows its secret key. So in this case, we should require the predicate equal to 0. The second one is the malicious case. In malicious case, the public key wasn't given in previous oracle, which means it was generated by the adversary itself, and the adversary has its secret key. So in this case, we require the malicious public key is valid, and the predicate equal to 0. The last one is the honest case. In this case, the public was given in Oracle generate, but wasn't asked in Oracle prop because the adversary doesn't know its secret key. In this case, we allow the predicate equal to 1. If all these requirements is satisfied, the challenger will aggregate and encrypt one of the message. We said the slotty registry AD is secure if the adversary has no idea which message was encrypted. And compared with current work, our work is the first generate black box construction on the killing assumption. And our construction can imply some concrete scheme on the killing assumption and in the prime order group. I should mention that the registry IPE from our work doesn't achieve the triple hiding. This is suffered from some property of predicate encodings. Well, I'd like to look at the notion of predicate encodings. For some predicate P, the predicate encodings consist of 4 metrics. They are CX, KY, AY, and DXY. Given value X and Y, these metrics can be computed deterministically. Write CX, KY, and AY together as a matrix MXY. The predicate encodings have these two properties. When predicate equal to 1, it satisfies alpha reconstruction. This property usually used to provide the correctness. And when predicate equal to 0, it satisfies alpha privacy. This property usually used to assure the security. We will start our overview from the 1-key standard ADE in composite order group. In standard ADE, CX is embodied in separate text. KY and AY are embodied into the secret key. In encryption phase, the computation will use the DXY in predicate encoding as we show. When predicate PXY equal to 1, use the alpha reconstruction of predicate encodings. The decryption can go through and recover the message. Start from the standard ADE. We now move to the zero slope registry ADE, where no user will reject at all. The highlighted in decryption equation spell that we can embody Y into the master public key, so that into the ciphertext. If you look at our zero slot registry ABE, you will see the structure of ciphertext is very similar to the decryption equation where we highlight. So the decryption is just like in the standard ABE. It can reveal the message well with alpha reconstruction if the predicate pxy equal to 1. Next, I will talk about how to modify the zero slot scheme to allow the user to reject. Similar to HLWW23, the user will generate an L gamma key pair as its public key and secret key. For registration, we will replace the alpha with alpha plus u in master public key and ciphertext. In decryption, the first step is similar to the zero slot scheme and can recover distance in green with the alpha reconstruction. Then, the user for the secret key can recover the message just like in the L gamma encryption. As we mentioned before, we should consider three cases of slot in the security model. Here, we only consider the honest case and the corrupted case, and I will talk about how to handle with malicious case later. In honest case, the security isn't leaked and we allow the predicate equal to 1. In this case, the security is similar to L gamma encryption with the fact that you can hide alpha over group. In corrupted case, security is leaked and we require the predicate pxy equal to 0. In this case, the alpha privacy of predicate encodings can hide alpha, and this can provide the security of our one slot registry ABE. Then let's talk about how to build a many slot scheme. We first simply generate L parallel one slot instance and put their CLS together. We get a CLS for L slot scheme. For registration, we first let each instance register respectively and obtain their master public key. With this one slot master public key, we add them together and get the L slot master public key. In particular, we obtain the L slot scheme as follows. Note that the ciphertext is encrypted from the aggregating master public key. So there is a question. A user with slot I and hold a secret key, can he successfully decrypt when predicate pxy equal to 1? We observe that given a slot index, the first three terms in ciphertext can be decomposed into these two parts. We call them local part and mixed part. For the user in slot I, the local part is exactly the ciphertext of one slot scheme, and the mixed part contains the terms from all other users. As you remember, the local part can be handled with the user secret key, just like the decryption in one slot scheme. So the question is transformed to how to remove the mixed part. As I introduced in definition, in slotted registry ABE, the decryption phase needs the hyperkey as an additional input. Exactly, the hyperkey is designed to remove the mixed part. A naive solution to set hyperkey is as follows. However, this solution will suffer from the mix and match attack. Notice the aggregate algorithm in slotted registry ABE is the deterministic and public, which means the the hyperkeys are public. In fact, if we design the hyperkey in this way, the user in slot I can use all hyperkey along with its secret key to recover alpha I over VP. This is not allowed and will make our scheme broken. To fix this problem, we use the idea of constructing collusion resistance in standard ABE. In particular, we need to introduce different random points into each hyperkeys. This can avoid this attack, and this solution needs a bilinear group and pairing. In fact, we embody hyperkey HSKI into group GT with the random point I and embody the first three terms of master public key and ciphertext into group G1. Similar to standard ABE, the last term in ciphertext is embodied into group GT. Now, the user in slot I can use its hyperkey to remove the mixed part of ciphertext. And when predicate equal to 1 with his secret key, the user in slot I can decrypt the local part and recover this SRI alpha I over group GT. However, the last term in ciphertext is as we highlight here. This user still cannot recover the message. For successful decryption, we have to include all I alpha I over GT into the master public key so that the SI alpha I into ciphertext. But this will make the size of master public key grow up to the linear of L. This is not allowed in slotty registry ABE. Actually, the size of master public key should be limited into polylog L. We use a trick in standard ABE to deal with this problem. We include a new alpha via this term we highlight into the ciphertext and connect the alpha to alpha I with this term we highlight into HSKI. With this trick, the user in slot I can recover the message as follows. For summary, we get the LSO registry ABE as follows. To achieve the security, we need to embody this scheme into composite order group, and we have to omit the detail here. Next, I want to mention a connection of registry ABE to the broadcast encryption. In fact, some recently work point out that the registry ABE can imply some broadcast encryption, such as distributed broadcast encryption. And use the composite to prime order transformation. You can obtain the LSO registry ABE in prime order version as follows. To prove its security, we need a dual system technique for standard ABE in the proof. In fact, we view hyperkey as a secret key in standard ABE. And since the aggregation is deterministic, we actually deal with the CRS in the real proof. If you remember, we only consider the security without malicious case in previous game. Now I'd like to briefly explain how we handle with malicious public key. In dual system proof, we need to simulate CU over group. But if a change public key is malicious, the challenger will think it as a matrix T and doesn't know the secret U behind it. So he cannot simulate CU without U. To fix this problem, we include an actual term R into the CRS and Q equal to RU into public key. In reduction, we can invert C into CRS and so that CU into the matrix Q. So we can recover the CU from Q, even if the U is a none. With this actual term, the adversary may submit an inconsistent public key, where matrix T and Q are computed from different U. To avoid this problem, we employ the QANIZ key, and that is how we handle with the malicious public key. The last thing is an open problem, and that is all of my talk. Thanks for your attention.
Thank you, Drew, for the talk. And now we have a question. I want to ask a question that why your registration-based IPFE cannot achieve a trivial ID because you use the predicate encoding with particular type.
But that's a very important question. This is because our construction is generally and in our real scheme, the decryption will need the CX and DXY from predicate encodings. To compute these two terms, we require some knowledge of value X. So even with the attribute high predicate encoding, we still need some knowledge of value X to decrypt. So this is why the registered IP from our construction cannot achieve the trivial hiding.
Any other question?
Well, you said in your construction, the length of master public key should be limited to be polynomial in log L. I want to see the reason behind that. Because we always construct attribute-based encryption without considering this restriction.
This is because our final purpose is to build a full version of registry ADE. And to build a full version, we will use the slow T version and via approach which called the powers 2 that's from HLWW23. If the size of master public key is the poly L, then the size of master public key in the full version maybe become the hyperpoly, and this is not allowed. So we have to limit the size in poly log L in the slow T string.
Thank you.
We have no more time for questions, so we can discuss offline. So now we move to the second talk in this session. It's about register in the product function encryption. The author Daniel Francati, Daniel Friolo, Monsoji Maitra, Julio Malavota, Almadera Dahimi, and Daniel Beturi. And Daniel Friolo will give the talk.
Thank you so much for introducing me. I'm Daniele Fiolo, and today I'm going to present a registered in the product functional encryption. And this is my joint work with Danilo Francati, Monsoji Maitra, Giulio Malavota, Almadera Dahimi, and Daniele Beturi. I want first of all to thank the previous presenter to give a warm-up of what are the definition of registration-based encryption primitives, so that the audience overall can maybe understand a little bit. Let me first introduce functional encryption. So in functional encryption, let's say that a player, let's call them Christy, wants to encrypt a file, and now whoever owns the encryption key related to some function can actually learn the function applied to the plain text and nothing else. Usually, how it is modeled is by the existence of a trusted party called public key generator, actually holding a master public key and a master secret key. And that each time a user wants to obtain an encryption key related to some function, he will handle the function to the public key generator, and will receive the decryption key for that particular function. So, of course, for functional encryption, essentially what we need is that if the adversary can actually learn a certain polynomial number of decryption keys, there is no way for the adversary to learn any other function in the plain text except the function related to the decryption key that you learn. Essentially, the main problem of functional encryption and all the primitives like IDE and ADE is that there is a single point of failure that is the public key generator. So that essentially the problem is that the master secret key might be leaked, and we want to avoid it. So essentially what we want to do is to create something more similar to a standard public encryption scheme in which essentially we try to remove or at least relax the power of the public key generator. So what do we have in registered functional encryption? And of course, this definition is based on all the previous registration-based works. Now what we have is a key curator. And what the key curator does is generating a master public key. And now instead of generating the encryption key by itself, it is going to receive public keys generated by each player and the function associated with each public. So now only the users will know the secret key associated to the public key, and upon encryption can actually decrypt and learn the function of the plain text by using their own secret key together with the master public key. So this master public key is updated periodically and handled to the players, so that the players can encrypt every time with updated master public key. And also the public keys handled by the players can be also marked for. Of course, a trivial solution would be to just embed all the public key that the key curator receives inside the master public key. But the problem here is that now the master public key depends on the number of users, and this might be highly inefficient and we want to avoid it. So this is one of the main goals of registration-based primitive and registered functional encryption. So how it is modeled actually in an algorithmic sense for the algorithm is that now the key curator updates the public key periodically, but at each update is going to also release a key called helper secret key to each of the players that essentially connects each update of the master public key together with the public key of the ith play. So which are the requirements? We require that essentially the CRS generated at the very beginning by the key curator, the helper secret keys, the master public keys must have polylog size and the number of users. And the very same we require for the key generation and the registration the registration key algorithm to run polylog time. And also we require that the number of updates is sort of independent of the number of users, so we require that the number of updates must be log L at most. So in our contribution, we have two main contributions in our paper. First of all, we define a registered attribute hiding inner product encryption from prime order groups in the bilinear generic group model. In the context of registered functional encryption, it can be recasted as this particular function that is essentially a function who has embedded a vector x and takes as inputs the message and the vector y, and either outputs the message if the inner product is 0 or bottom otherwise. So, and this is how we require attribute hiding, essentially meaning that y must be also must remain secret, even upon decryption, and also when there is no when the ciphertext is not encrypted. Also, we define a general, so we construct a general scheme for registered functional encryption for generic functionalities and also a large universe of users from an indistinguishability obfuscation and somewhere statistically binding hash function. So the blueprint of our construction is similar to the one of the former scheme for registered attribute-based encryption of Hohenberger et al. And I'm going now to show you how our main contribution here works. So first of all, let's compare our protocol. We did a comparison with all the registration-based protocol, but mainly with the registration IDE of Hohenberger et al. So essentially, with respect to them, we have a large function space, in particular n-size vectors. Instead, they have a small attribute space. They require a small attribute space. We also achieve strong attribute hiding, also called CPA two-sided security in the context of predicate encryption, whereas they need attributes included. As cons, of course, whereas Hohenberger et al. Do they make contributions for all efficient contributions for all the linear secret scheme policies. We are for the only we are constructing RFE only for inner product, and we also require the generic group model when instead Hohenberger et al. For Hohenberger et al. It's sufficient for pairings in the standard model, but in composite of the groups. All of us actually require an unbounded number of users, and also that the CRS, the key general registration time, are actually dependent on the number of users, but it is still fine since the communication complexity for handling master public keys and adversarial keys is still wholly low. So we did a comparison with, at that time, all the registration primitives that we know, and especially you can see here, for example, the size of attributes needed by Hohenberger et al. Is all the universe of attributes, so only works for small attributes, when instead we just require the size of the vectors for our complexities, and so on and so forth. Okay, let me introduce now our main contribution. So we prove our scheme for slotted RFE. So similarly to slotted ABE, now the key curator will receive at the very beginning all the keys related to the function or from each player in the system all together. So essentially the number of users is fixed at setup. So we know the number of users at setup, and all the public keys are indexed in some slot, and then all the data structure containing of the slots is aggregated with an aggregation algorithm that will be essentially a single short master public key to be handled to all the players. So here we are only one update, but also we are dependent on the number of users. So in order to achieve generic registered functional encryption, we can use actually the compiler, the very same compiler of Hohenberger et al. With some slight modification to compile the slotted RFE to a standard RFE with log L updates. So this is the rough idea of how it works. Essentially, what we have, the trusted part, the key curator upon generating the CRS will first of all generate all the parameters for the primordial queue and the pairings. Then as general parameters, we also have a value h. There is a random the group G1 raised to a random beta, and then the pairing raised to a random alpha. And then what we have are slot-specific and key-specific values. The slot-specific values are essentially a value A, that is G2 is a random T, and a value B, that is essentially a connection, that essentially connects A, H, and Z. So the general parameter with the other slot specific parameter. And moreover, we also need n+1 key specific values that are essentially G1 raised to some random value W for n+1. Why we are doing this for n+1? Because essentially in our scheme, we are treating all the components of the X vector given together with the public key in the single slot together, we are considered together with the secret key. So essentially the secret key can be seen as part of the vector X itself. So indeed, the public key is the following, is the last U n+1 value raised to minus S key. And to do the key aggregation, we just multiply the public key with all the UW terms raised actually to the X components. So this is just our map. So what do we need to actually calculate to actually construct the single slot RIP? So for encryption, first of all, we have these two terms that essentially are used to create a mask of M with this particular pairing here, that is E H to the S8. So the main point here is to make the decryptor recalculate that H to the S in such a way that the only way for him to calculate such particular H to the S is by knowing, of course, a vector Y that is orthogonal to X and the secret key related to his own public. How we do that? We essentially we define ciphertext components that are all the ciphertext components that are related to the component of the Y vector, re-randomized, multiplied by this H to the S, and then multiplied by the key specific terms raised to some minus. Then we have this n+1. And similarly, we have H to the S multiplied with this very same value, but only for n+1. And then still for n+2, we have H to the S multiplied by the aggregated public key raised to -z. So why do we need this? So essentially, we need this because here what we do, we are raising this term here to the secret key, and this term here to all the components of X. This is what happens. So essentially, if you want to decompose this, we can see that all the terms cancel out. So essentially, the aggregated secret key, this term here, will cancel out with this term here, that they are both, this was raised by all the X component before, and here we raised to the X component, so we can cancel them out. And the same here, because the public key is the n+1 terms raised to the secret key, and here we raise the n+1 term to the secret key, so they cancel out. Last thing that is remain here is the multiplication between all the S component to the Y component in the exponent here, because we are essentially raising the Y components to the X components. So, and they are also randomized by this randomizer R. So essentially, for inner product, since the inner product must be 0, also this terms is going to cancel out. So what remains here to calculate H of S is just the secret key and all the XW terms that are part of the decryption. So we are fine. So now, of course, the main problem is to extend it to 2 slots. I will just give a very rough idea of how it works. So the idea essentially is to, the rough idea is to just do the key aggregation as before, but now we aggregate all the public keys and also the key specific slots for all the raised to the related vectors, x1 and x2, multiplied together. But of course, we are going to have some cross terms that we must eliminate. Let's say that we are player 1, we want to use the secret key 1. Blue terms are going to cancel out, the square terms are not. Essentially, what we do, we introduce new cross terms. We essentially are trying to relate the key-specific slots, the slot-specific values in the CRS together with the key-specific values of the CRS. Essentially, we are raising them to the exponent of the other key-specific slots. So by adding them and raise to the secret key in the public key, and by multiplying them and put them in the helper secret key, essentially, we find a way to cancel them out. Okay, and also, of course, we have to add another ciphertext to make all the magic things here happen. So of course, I'm not going to do this for this since we don't have time. To conclude, what we saw is a registered functional encryption definition. Then our construction for registered IP from pairings in the generic group model. And in our paper, we also have registered RFE for pure poly and a bounded user from IO and SSBS function. What is left open, essentially, we are wondering whether it's possible to construct RFE from any compact and polynomially hard functional encryption, or like specialized function classes, but from weaker assumption. And then, of course, we are using the GGM. It would be really nice to prove registered IP in the standard model. So thank you for your attention, and happy to answer to your questions.
Thank you, Daniel, for the talk. And now we have time for questions.
So thank you for the talk. So as I see, you formalize the definition of registered functional recursions to avoid the TS-scroll problem. But as now the TS-scroll problem seems to be a problem in the functional recursions where the encryption key is public. Do you think the registered functional recursions is useful for the private key functional recursions?
It's less useful, okay, because we are using secret keys, but it might be still useful for like in the settings where you want to protect player owning some secret key from other player owning other secret keys. Still, you can define it in this way. So like one of the secrecies of the specific secret key of some player with respect to the secret key of other players. So maybe we can take it offline for the details. There is a way also to define that for the secret key setting.
The question? So you mentioned that one of the shortcomings is that you can improve the security in the generic group model. Can you explain why you cannot prove?
I mean, we just mainly because we didn't find a way to prove it in the standard model. The main reason is because, of course, we use the same blueprint of Weinberg et al. But at some point, we just did it from the protocol, since we are, in order to achieve attribute hiding, we essentially including the secret key as part of the vector, as I was saying before. So, and essentially, we don't know how to prove all security, in particular attribute hiding, without relying on the generic model. So we just didn't find a way to prove it.
Okay. Other question?
So as you have mentioned, it's only the attribute hiding property in GGM. Other properties in GGM as well, or
I mean, like, yeah, I mean, like, I didn't work. I wasn't the only one working on this proof, so we can continue flying. Sure. To talk about quality for this. Yeah.
We still have time for question. No more questions, so let's thank the speaker again. Now, the first talk in this session is about what we decentralized client function encryption. And so the author is Yamei Li, Zhang Hongwei, Fu Chunzhou, Yi Sucio, Xiaotong James, and Yamei will give the talk.
Thank you for the introduction. Good morning, everyone. I'm Yan from Xi'an University. I would like to introduce a new functional encryption. My title is Robust, Decentralized, Multi-Client Functional Encryption, Composition, Definition, and Inner Product Constructions. This is a joint work with Wei Jiahong, Guo Fuchun, Wei Susila, and Chen Xiaofeng. Now, first, I will start with the introduction. Functional encryption, as in short, can finally control the amount of information that is revealed from a self-test. In FE, there is a key generation center, KGC, who generates the master secret key, MSK, and the master public key, MPK. The data owner, who encrypts the private data X and sends it to the data user. Finally, the data user can obtain the function value fx if he or she can obtain the functional key SPF from KGC, where the functional key SPF was generated by using the master secret key MSK. The security of FE guarantees that the data user can only learn fx and nothing else about X. Multi-client functional encryption, MCF in short, can aggregate information from different data owners. In MCFE, KGC generates an encryption keys and distributes EKI to each owner. And the label L, each owner uses EKI to encrypt the private data XI and sends it to the data user. When all cybertests correspond to the same label, the data user who obtains the functional key SPF can obtain this multivariate function value. Decentralized multi-client functional encryption, DMCFE in short, removed the trusted third party. In DMCFE, setup protocol, owners interactively generate the encryption with API and the secret with SPI. Similarly, each owner uses API to encrypt the private data XI and sends it to the data user. Since KGC is not involved, the data user sends the function to each owner. Each owner who uses the SPI to generate the partial functional key EKI and sends it to the data user. Then the data user combines the partial functional key and obtains the functional key SPI. Through the decryption algorithm, the user can obtain this multivariate function value. We can find that the concept of functional encryption has been continuously expanded. In FE, the functional key is generated by KGC, and the user learns the specific function of encrypted data from a single owner. Well, MCFE allows the user to learn aggregate information from several different data owners. In the MCFE, is not involved. The functional key is generated under the control of all owners themselves. Second, I will introduce our motivation. Our motivation is based on DMCIB, which has a wide range of applications. For example, DMCIB was used to measure at an underground station to detect the congestion. In these applications, each client inputs the private data outside, which is 0 or 1. One indicates the client has visited the station, and 0 indicates the client has not visited the station. Later, each client provides a partial functional key for the letter 1. This letter is fully filled with 1, and its length is equal to the number of clients. Then the central server combines the partial functional keys and obtain this functional key. Through the decryption algorithm, the central server can obtain this inner product of x and y, where the vector x is composed of location data from all class. We can find that the inner product is just the total density and represents the number of class passing through that station. However, DMCIB requires that the server must collect the partial functional keys and subtext from all classes. When some class accidentally go offline due to hardware issues or intentionally stop participating, we call them native class. The central server cannot obtain the functional key and cannot obtain the traffic density. Even if only one client is native, server can still obtain and useful information. As the saying goes, a pot of milk is ruined by a drop of poison. A more realistic requirement is that even if some clients are native, the central server can still calculate the data from positive owners. So, an interesting question arose literally. Can DMCIB still work even when some clients don't generate partial functional keys or input their sensitive data? We solve this problem by introducing a new definition for the robust decentralized multi-client functional encryption, RDMCIB in short. This figure shows our algorithm definition, which is based on the definition of DMCIB. An RDMCIB scheme is composed of a setup protocol and 3 algorithms. So that in the motivation, to detect the congestion as realistically as possible, we require that the number of positive classes is not less than a given threshold key. So in the setup protocol, we additionally include the threshold key, which limits the difference between the function values in the robust and non-robust settings. Second, the partial functional key generation algorithm additionally includes the label L and the set of positive classes, where the label L achieves fine range as control, and the set S declares the state of each class, so that the partial functional key can eliminate the influence of native classes. To have robustness, the decryptor does not need to obtain all partial functional keys and subtext, but a subset of partial functional keys and subtext. To run the decryption algorithm and obtain this function value. In this fashion, some inputs may be the predefined default value at 0, since some class are negative. X0 is used to unify the expression of the function in the robust and the non-robust settings. The security definition of RDMCIB is also based on DMCIB. Our security definition is much more complicated since we need to consider the state of the data. In this security game, the adversary chooses the set of corrupted class CS. In other words, the adversary sends the degeneration queries. When only one degeneration query was sent, it responds to one ID security. Otherwise, it responds to many ID security. Finally, the adversary sends a challenge to each client. Note that all corrupted class xi0 must be equal to xi1, and these two function values must be equal. Otherwise, the adversary can truly win the security game. The security definition of RDMCIB is also based on that of DMCIB. Note that for robustness, the degeneration of additionally includes the legal and the set S, and only outputs the total functional list of possible owners. Furthermore, the security restriction was changed from XI to XI prime since some inputs leave separate value for the value at 0. First, I will introduce our constructions for inner product IP in short. Our constructions have three steps. First, I will remove the special IPMCIB has robustness. Second, based on special IPMCIB, using button masking structure, we designed our basic construction that has one ID security. Third, to enhance the security, we designed an enhanced construction that uses exact single masking structure, a homomorphic secret chart scheme, and an inner product functional. Before that, in IPMCIB, data is represented in the form of vectors, and the function is a vertical transformation of the vectors. The user learns the sum of n product, which is for the morphing of the inner product. In special IPMCIB, the master secret key MSK consists of n encryption keys that, and each encryption key that consists of a value SI and a vector UI. The functional key SY consists of n values SIY and the sum of n inner products, where the value SIY is a function of SI and the vector YI. We found that the special IPMCIB has robustness when the decryption algorithm only includes the functional key S1 and a subset of ciphertext. The decryptor can obtain the most input inner product corresponding to the cipher S. So we define the robust correctness and the robust security. Furthermore, we proved that if the special IPMCIB has static ID security, it also has the robust security. Intuitively, IPRDMCIB can be constructed from special IPMCIB if each owner generates the virtual functional ZKLY, which consists of SIY and the inner product of UI and YI. the decryptor cannot obtain each inner product of UI and YI. So in the basic construction, we use the mask Ri and Wi to mask the inner product of UI and YI, where the mask Ri is randomly selected by the owner I. So the sum of for I belonging to S, the sum of inner products of UI and YI is equal to the sum of MKI minus the sum of Ri and minus the sum of Wi, where the mask Wi is computed by VIG, which is generated by our non-interactive case scheme, NIG in short. Since the correctness of NIG, we have VIG is equal to VGI. So the sum of N masks Wi is equal to 0. That is the sum of Wi inside S plus the sum of Wi not in S is equal to 0. So the sum of inner product in subset S is equal to the sum of MKI inside S minus the sum of Ri in S and plus the sum of Wi not in S. To calculate this formula, the user needs to obtain Ri of positive owners and Wi of negative owners. So for each owner, the user can only obtain one mask, that is Ri or Wi. Well, another mask can still produce the inner product of UI and YI. That is why we use the double masking strategy. To obtain the mask Wi, the user can obtain NSPN. So the user actually needs to obtain Ri of positive and NSPN of negative. For robustness, Ri and NSPN are shared with other owners who are threshold sharing scheme. In this way, as long as the number of positive owners is not less than a given threshold, even if some owners are negative, the user can still obtain shares from positive owners as part of the desired information. Specifically, to generate and share the masks Ri and Wi, each owner runs the key generation algorithm of NIP to generate NSPI and NPI, and selects a random value Ri. The owner one shares the NSP1 and the R1, and since the NPP1 a share of NSP1 and a share of R1 to each owner. Every owner does this. Finally, each line of each list, each owner puts the NPPI and a pair of shares. Using NSPI, the owner I can compute N-1 shared case VIG. Using VIG, the owner I can compute the mask Wi. Second, to help the user to reconstruct the desired information, when generating the partial functional key VI, by observing the state of each owner, the owner I decides which share to be revealed in each pair. For example, if only owner 1 is negative and the others are positive, if positive owners reveals this unhighlighted shares, if the number of positive owners is not less than the threshold T, the user can construct this value are used to compute W1. So the user can calculate this formula and obtain the DQI. The DQI is the part of functional key SQI file in the special IPM CFE. Now I will summarize my talk. Based on the previous work, we introduced a new notion that is robust decentralized multi-functional encryption, and which achieves the robustness of DMCFE. Furthermore, we introduced two new properties for special DMCFE. They are robust correctness and robust security. Finally, we proposed two constructions for inner product. Due to time constraints, I have omitted the enhanced construction in this photo. If you are interested, you can read out. Thank you for your attention.
Thank you, Yami, for the talk. And now we have time for questions.
Your enhanced construction, you use homomorphic secret sharing. I want to know that how many degrees of your homomorphic secret sharing support. Is degree 2 homomorphic secret sharing enough?
The threshold is given in the setup protocol. That is fixed.
Other question?
Hello, I have a question for the security, which you mean two kinds of security. One is the one ID security, and the other is the many ID security. If they are equal.
Thank you. One is security is the key generation queries is limited one time, and many anti-security is the adversary can access many key generation queries. This is the difference. That is not equal.
Other question? I have a question. Can you go back to the slide 27? The slide 27. Yeah. So suppose that there are some users who go offline, and so in that case, they are not in the corrupted user, and they are not either in the set test. So you need some restriction on the non-corrupted users and not in the packet.
The set of possible before the generation queries, before the generation oracle, that each class interact with other class the state of each kind. So they can obtain the set of positive owners. They are intertide with the others and obtain this set.
Yeah, but the set S does not cover the offline user, right?
The set S is the online user.
Online, and so does not cover the offline user, and the corrupted set doesn't cover offline user either. So I don't know if because the set CS and the S does not cover the whole universe of users.
CS is a set of correct
Correct,
class, and the S is a
Online.
set of online class.
Yeah, and how about the offline users who are not corrupted and not in the online set?
Yes.
Other question?
About which problem does this work this be resolved?
Our solution is the generator cancellation. The issue security is based on the security of the underlying truth. The basic construction uses the underlying tools such as the non-interactive exchange scheme and threshold secret sharing scheme.
So for this security definition, the corrupted set is chosen at first. So it's like more of a passive security definition. Is there an adaptive version of the security definition that you have considered?
No, I didn't know to consider this aspect.
So let's find the speaker again. So now is the last talk in this session. It's about cuckoo commitment, registration-based encryption, and key value map commitment for large space. And the author are W. Fior, Dimitri Kolonelos, Paula De Petrus, and Dimitris Digital Talks.
Okay, hi everyone, and thanks for attending the talk. So let me try this. Okay, good. Okay, so thanks everyone for attending. Again, I'm Dimitris Kolonelos from India Software Institute, a PhD student. And this is a joint work with Dario Fiore, my advisor, and Paula De Petrus, who should be somewhere, at least she's at Asiacrypt for sure, and probably she's somewhere in this group. Okay, so the outline of the talk will be the following. First, the motivation of the work, which basically our main motivation was registration-based encryption. Then briefly, I will state our contributions. Then our main technical contribution is our RB compiler. Then a secondary result is our key value map commitments compiler that I will describe, just mention briefly. Then at the end, some conclusions and open problems. So yeah, let me start with the motivation. So the motivation of the set is registration-based encryption. I guess so the previous speakers made a really good job at explaining what exactly registration-based encryption is. So probably I have to go fast. So one step before registration-based encryption is the identity-based encryption, in which we have encryption and encryptors and decryptors, and the encryptors want to encrypt with respect to an identity, which is an identifier of the user. So for example, I don't know, a name, a username, a phone number, whatever. It's an identifier which is not a cryptographic value, like a public key. And the encryptor wants to encrypt only by having this information. So the way that it works is the following. We have a third party that we call the private key generator that generates a master secret key and the master public key. The master public key goes public, and then the
parties that want to participate as decryptors come and say to the private key generator, please give me my secret key. And the private key generator is actually doing exactly this, is using the master secret keys, generating the individual keys, and passes them to the corresponding users. And after that, everything works as promised, that an encryptor can use the master public key to encrypt with respect to an identity so that only this identity is able to decrypt. Actually, for security, we demand that even if all the other users, except for the identity collude, then still the ciphertext remains semantically secure. And there is an important property that I call non-triviality, which says that the master public key should be succinct, should be much smaller than the number of the decryptors in the system. Otherwise, identity-based encryption could be trivially realized by public key encryption. Okay, so this is IB, which is a very well-known primitive, of course, I guess most of you are aware. But I guess also most of you are aware, and as the previous speakers also denoted, of the key escrow problem, which is a notorious problem that is kind of obvious that this part, the private key generator, is super powerful. The private key generator can decrypt all messages, knows all the secret keys of the system. So this is typically normally a very heavy limitation of identity-based encryption in some scenarios. So for that, in 2018, Garg et al. Introduced the notion of registration-based encryption, where basically the encryption works as an identity-based encryption, as before, except now the users are locally sampling their secret keys together with a corresponding public key, and they're sending the public key to another third party that we call the key curator. So what the key curator does is that it takes the public keys and compresses them into a small representation that we call the public parameters, which is the analogous of the master public key. And the thing is that, whatever the key curator does is fully deterministic. It requires no secrets. Here I forgot to say that the key curator, but I guess the previous speakers highlighted it, that the key curator needs to pass some helping information to the users that will help them to decrypt the messages, which again, the helping information contains no secret. It's something that can be computed deterministically. In any case, the key curator is fully untrusted, fully transparent, and it's only there just for efficiency reasons, to make the lives of the encryptors and the decryptors easier in terms of efficiency. There's another aspect in registration-based encryption, which is implicit, that we have a one-time setup, that sometimes it's a uniformly random string, which is the good case. In some other cases, we have a structured reference string. So this is it with registration-based encryption. Now, going to the constructions, the actual constructions of the primitive, the early realizations of the primitive, well, relying on heavy cryptographic tools, such as indistinguishability obfuscation or hash garbling, which is a very nice cryptographic method. Really, I would say, a breakthrough result. However, these solutions were mostly theoretical solutions, like feasibility results. They were really inefficient. For example, even indistinguishability obfuscation, I guess it goes without saying that it's a very inefficient primitive. For hash garbling, even if the assumptions there were kind of optimal, I mean, if not optimal, they were really light. The thing is that even with hash garbling, we could have ciphertext in the order of terabytes. So basically, this primitive was kind of let's say, theory. Now, recently, we have a new generation of registration-based encryption, actually this year. So the work of Dodling et al. At Eurocript this year introduced a lattice-based registration-based encryption, which is much more efficient than the one of the previous works. It's kind of a black box, even if I don't know if this term is okay over lattices, but in any case, it's an efficient construction, which is not that efficient. I mean, it's more efficient than the previous ones, but lattices are typically large, they're huge. So still a ciphertext can be in the order of maybe gigabytes. Then there is the work that the previous speakers mentioned extensively, which is the one of Hohenberg et al. That introduced registered attribute-based encryption, which is a generalization of registration-based encryption for it's the analogous of the generalization of IDE to ADE. In any case, this construction is kind of efficient, but not completely efficient. So, for example, it inherits the complexity of attribute-based encryption. And also, I would say a limitation is that the setting is composite ordered by linear groups, which in practice it's much more inefficient and requires a trusted setup. Now, today the most efficient, at least prior to our work, the most efficient registration-based encryption scheme was the one of GKMR that appeared last week at CCS, which is actually very efficient. Everything runs smoothly, but it has the limitation that the identities are polynomially bounded. The space of the identities is polynomially bounded. So our main question, our starting question was that can we have something as efficient as the GKMR RBE, but with unbounded identities? And going to our contributions, actually our most tangible contribution is that the answer is affirmatively. We say yes, we provide an efficient pairing-based RBE construction with unbounded identities. We claim that it's today the most efficient RBE, and with unbounded identities. And actually, for that, we constructed generic compiler that boosts any bounded identity space RBE to an unbounded identity space RBE. And we also, in another result, we also basically observe that the same technique can be applied to boost the vector commitment to any vector commitment to a key-value map commitment, which is an independent result, for which we also provide a generic compiler. And technique-wise, we make a novel use of cuckoo hashing that we find interesting and we hope to be of independent interest. Okay, so our main technical contribution, our RBE compiler. So the core idea is actually very simple. It says, what if we take the identities from the large identity space and map them to a small identity space, and then use the RBE that we have for a small identity space? That's actually the vision, which is quite neat. However, of course, it's easier said than done. And the reason is that we know very well in cryptography that when you map large elements to a smaller polynomially bounded space, then collisions appear. Now, the question is how do we overcome the collisions? And here comes this data structure from computer science that is called cuckoo hashing, which is a very powerful probabilistic technique that does actually exactly this. Takes elements from a large space and map them to a small table, a polynomially bounded table. So basically, in cuckoo hashing, there are no collisions. It can be seen as a way to hash elements to a small space without collisions in a collision-resistant way. But there is a probability that the element will not find its way in the table, that the element is not going to be hashed, let's say. And this probability is typically non-zero, and we'll see how to handle with this probability in our construction, in our scheme. And cuckoo hashing actually uses k normal hash functions and the idea of evictions. Let's see how it more or less works through an example, which is, I think, the simplest form of cuckoo hashing is the following, where we have two hashes. And in this example, let's say that we have 4 elements and we want to insert a 5th element in the table. So what cuckoo hashing does is that it takes the 5th element, hashes it with the first hash function, h1 of x5, and puts it in the corresponding position that the hash indicated. Now the thing is that since the space is small, maybe another element was there because these hashes are going to have collisions, the individual hashes. So if this is the case, that another element was there, then x5 somehow evicts the previous element. And for the previous element, what we do is that we use the opposite hash function to indicate the next position of the element that was evicted. So for example, if x1 that was evicted was using h2 to go to the position, to the corresponding position, now we are using the opposite hash function, h1. And we continue like this until there are no evictions, and this is very let's say, a high-level overview of, like a high-level idea of cuckoo hashing. And what is important in our case is that actually in cuckoo hashing, we can deterministically say what are all the possible positions that the element can be. So we know that if we want to insert an element, this is going to be, for example, in this cuckoo hashing scheme, either in H1 of X or in H2 of X. We know deterministically all the possible positions that the element can be. And this is very important. So if we were to apply this for our compiler, basically what we would do is to take the identities from the large identity space, map them to a small identity space with a cuckoo hashing, use the RBE for small identities in order to generate the public parameters. And then the question is, how do we encrypt? Because the encryptor doesn't actually know how the table looks like. The encryptor only knows the compressed public parameters. So the thing is that the encryptor doesn't know which of the hash functions were used for the identity that she wants to encrypt. So an idea would be the following. What if we just encrypt with respect to all the possible positions for all the hash functions? So this is correct, because at least in one, we have the identity, but it's, I think, obviously not secure, because the thing is that, okay, in one of the positions, only the corresponding identity that we want is able to decrypt, but in the rest, maybe another identity is there. And this is something that the encryptor doesn't know. So of course, this identity will be able to decrypt something that is not supposed to. Okay, now towards the solution, we introduce something that we call in the paper witness encryption for vector commitments. In a nutshell, vector commitments is a well-known cryptographic primitive with which you can take a vector and generate a compressing a succinct commitment so that you can later provide an opening proof for every position of the vector. Everything is succinct and nice. Now, witness encryption with respect to the vector commitment works as follows. The encryption takes the commitment of the vector, a position of the vector, and the value, a target value. And it says that, look, if at this position that I'm indicating this value, in this case, V star, is in this specific position, then you will be able to decrypt. Otherwise, if another value is in this position, then you will not be able to decrypt. This is a kind of witness encryption, let's say, for the specific relation. Now, the thing is that typically witness encryption is a very heavyweight and very scary primitive that we don't know how, I mean, general purpose witness encryption is something that we don't know how to realize efficiently. So the thing is that we saw in the paper that for this specific scenario, for this simple case, there are efficient constructions from Ericsson, from LWE, which are actually simply not that surprising. So there is no efficiency problem with this BCWE. And what we can do now for our compiler is that on top of what we had before, we add a vector of the corresponding identities. And we commit to this vector. We add this commitment to the public parameters. And then what we do is that we secret share the message. And for each possible position that the identity can be, we give two ciphertexts. One ciphertext contains one share of the message, and it's actually the RBE ciphertext as before. And for the other part, we put the other share of the message, and we say that if in this position, the actual ID that I want to encrypt to is there, then you will be able to decrypt the message, the ciphertext, and obtain the message. So why is this secure? The thing is that, as before, we know that at least in one of these positions, we have the identity. For all the other identities, we can assume that the adversary can decrypt the partial, the share. On the left, can decrypt the share of the message. However, the thing is that whenever there is another identity on this specific position, then the witness encryption, the statement of the witness encryption on the other set is not satisfied. So nobody is able to decrypt this ciphertext. And on the other hand, where the identity is, all parties, everyone is actually able to decrypt the corresponding ciphertext, but in this specific case, we actually know that the actual identity is on the left side to decrypt and get the first part of the cell. So this is our compiler. The outstanding point is how do we actually deal with insertion failures in cuckoo hashing. The good news is that this is actually studied in the literature, and there are cuckoo hashes with negligible soundness, with negligible failure, probability of failure, which is negligible is already enough for us. The thing is that in our case, it's a bit more complicated because sometimes in the literature for cuckoo hashing, they assume that the adversary doesn't have access to the representation of the hashes. In our case, it's totally not the case. So actually, we have to use something that is called robust cuckoo hashing, introduced by Yale this year at Crypto 2023, in which it says that if you have lambda hash functions, then there are the insertion failures happen with negligible probability, even if the adversary knows a priori the representation of the hashes. If this is not the case, for example, if the adversary can only selectively, let's say, choose the identities, then there is a more efficient cuckoo hashing technique. So for the actual sorry about that. Okay, so this is the final skills. What I want to highlight is that basically the resulting construction, our main construction is the one that is using robust cuckoo hashing that has an overhead of lambda in the ciphertext size, but it has unbounded identities, or we can have a ciphertext that doesn't have this lambda overhead if we assume that the adversary is selective. And we also saw that in the scenario, in the case of selective adversaries, we can also improve on the lattice-based RB of Dotling et al. Okay, so I think for the last part, for the key value map commitments, I just want to mention the result and then refer to the paper because probably not out of time. So the thing is that the key value map commitments is the generalization of vector commitments when we commit to a mapping between a key and the vector and the value. And then we want to ask later what is the value of a specific key. But these keys can be arbitrary. So this has been seen actually as a sparse vector commitment, the key value map, for which we can also use a cuckoo hashing to map the sparse vector commitment to let's say a dense vector commitment with polynomial size or a polynomial number of positions. And then we can use the same technique basically to open all the possible positions of the vector for the opening. Yeah, probably this concludes my talk. What I want to close my talk with is that basically the cuckoo hashing is very powerful and surprisingly underexplored in the context of public key encryption primitive that we would be very happy to see other applications of this. And I also have some open problems here. And in any case, thanks for the attention. And in case there is time, I can take questions. Otherwise, you can find either me or Paula somewhere in the conference. So thanks.
Thank you, Dimitros, for the talk. I was wondering how should we go over this? So, in this vector commitment, who is creating this vector commitment that commits all the identities in the table? Who's creating this commitment? The aggregator?
Yeah. The aggregator.
But then, so how come people can open? He gives them selective.
The aggregator this is a very good question actually. Thanks. So the aggregator is generating the opening proofs and it's putting these opening proofs in the helping information that we mentioned at the beginning. Because
so the proofs are what allows with the witness in the
representation. Exactly.
So each person has a proof that the vector commitment opens with their value.
Exactly.
And you actually can do an efficient, so it's a meta thing. So I have a proof and I use the proof
to
open.
Exactly.
and it is efficient.
Yeah, that's why in some sense we say that, I mean, that's not actually a witness encryption, it's actually a witness encryption with the vector commitment, because you are taking the verification equation for the vector commitment, not the actual thing that the value exists in this position. So we are using the opening for the decryption.
And when the aggregator is rehashing, right, because he needs to
Yeah.
overrun, so then he needs to update everyone, right? So I have to keep on being able to be updated. And maybe, you know, the aggregator tells me, so I used to have some sort of witness, but now because the aggregator has shifted stuff around, I have to keep on consuming that updates from him.
Yeah, that's another very good question that I also made in this talk. So this is a problem actually in every registration-based encryption scheme, because previous registration-based encryption schemes were working with Merkle keys. So then you need to keep the path, and you need to keep the user updated with this path. So there is a very nice trick, like somehow it's relevant to this slotted version of registration attribute-based encryption, in which you can actually have a data structure so that the opening proofs are only updated log of n times throughout the system. So you don't have to update the opening proofs each time. I mean, there is a standard transformation that we mentioned in the paper. It's kind of complicated. I didn't mention it here. So there's a standard transformation to take this, that in this scenario, actually, the user should be updated each time that a new user arrives. So you can have another transformation, not from us, from previous works, in which you can take this and make it like the maximum number of updates for each user to be log of n instead of n. But this is actually a very interesting point. You this log of n of these vector commitments. It's a very nice trick, not ours.
Other question? So let's thank the speaker again, and all the speaker in this session. Yeah. It's very nice. Give another course to the instructor.
你好。